And it's a great pleasure to introduce another pioneer of neuromorphic computing, Professor Giacomo Indiveri, who is also our honorary chair. He is with the University of Zurich and ETH Zurich, and his talk is Bridging Natural Intelligence and Artificial Intelligence with Neuromorphic Technologies. And I think you will run this from your own computer.
Yes,
and whenever you're ready, please go ahead. Please welcome Professor Indiveri.
Thank you. Well, it's really an honor to be, first of all, honorary chair of this amazing conference. I really would like to congratulate the organizers for making such a spectacular program. And now, please, since we do have some time, please allow me to try to set up the laptop so that I can run the presentation from my laptop. I will try to connect with the HDMI. We did try it before, it was working. It should just be a few seconds. Okay. And I see it on my screen. Ah, here we are. Sorry, just... And as the title says, the plan is to try to give you an overview of what is required to bridge natural intelligence from natural intelligence to artificial intelligence. Again, I'm Giacomo Indiveri. I'm from the Institute of Neuroinformatics of the University of Zurich and ETH Zurich. We do work in this institute on both natural intelligence by doing standard system and experimental neuroscience. Oh, sorry, I'll take that away. If I manage to. Sorry about this. Okay, here we go. But we also work on artificial intelligence, or actually I should say on neuromorphic engineering, which is, as you will see, loosely related to artificial intelligence. And so the idea is really to show you what are the links between these. But even before going to the links, I would like also to take the opportunity to tell you a little bit of the history of the term neuromorphic and what that actually relates to. We've heard the term neuromorphic being used many times. The term neuromorphic was actually coined by Carver Mead in the late 80s, early 90s, to refer to a discipline that was investigating the computational principles of real nervous systems, of real brains, by using the physics of electronic circuits. And at that time, the mostly available technology was CMOS. So at that time, it was using essentially the physics of silicon and CMOS circuits. Carver Mead was an electrical engineer, or is an electrical engineer. He's retired now. Misha Mahowal was a biologist. Misha was his first student. And by combining their interests, they really decided to explore what could be done using, for example, diffusion in transistors, in weak inversion transistors, to reproduce the diffusion processes that happen in cells, for example, in the generation of action potentials from sodium and potassium channels. It was really the idea that you could emulate the biophysics of cells using the physics of transistors. And the transistors, instead of using them as pure zeros and ones, the digital, but if you use them as analog, and if you use them in this weak inversion or subthreshold domain, then the physics are exactly the same. There's Boltzmann statistics, diffusion, and therefore you get exponentials. Of course, silicon can also be used as a digital medium, and so you could combine the best of both worlds by using both subthreshold analog and asynchronous digital. This was, as I said, late 80s, early 90s, and I also take this opportunity to do a little digression to say that I actually was visiting Caltech myself in the lab of Christoph Koch, who you see here on the left. If I can use the pointer, yes. So I was in K-Lab together with other colleagues, among which Jörg Kramer, who was one of the first designers of silicon retinas after Misha, or if you want, the dynamic vision sensors that some of you might know about. I also met another one of the first students of CoverMe, Toby Delbruck, and then Shichi Liu, who was also a student at the time and who's actually the last student of Cover before he retired, who are now also with me at the Institute of Neuroinformatics in Zurich, working on the design and application of neuromorphic systems. In those years also, Misha Mahowald met the founder of the Institute of Neuroinformatics, one of the co-founders, Rodney Douglas, and together they designed a silicon neuron. This was, again, late 80s, early 90s. You see the really impressive achievement they got by designing an electronic circuit that could reproduce with great faithfulness the properties of real neurons, even gave them the cover of Nature. And here is a story to remember, because by this time, the community was so impressed that they were saying, if you can do a single neuron in silicon, then just by scaling up using the properties of VLSI, very large-scale integration technology, you will be able to finally build an artificial brain. This was sort of the reasoning. If we know how to do single neurons, we only just need to scale up, and we will get to brains. There were some efforts in building a silicon cortex system and some efforts in scaling up, but little did they know of the challenges that it takes to actually go from a single device, a single synapse or a single neuron, to getting the complexity and functionality of a whole brain. But sort of to go back to the term neuromorphic, the term neuromorphic was being used in these years to refer exactly to this basic research approach. But in 2008, Stan Williams, who will also be presenting here, made a very impactful publication on memristors. They found the missing memristor, and they also started to use the term, and the community started to use the term neuromorphic to refer to these devices, as we've heard, that are two electrode devices that can store information in a non-volatile way by applying a pulse, like a spike, to the bottom and top electrode, with some variability, with some state dependence, stochasticity, so with properties that resemble, in many aspects, the properties of real synapses. And therefore, because this was an electronic medium reproducing the properties of biology and nervous systems, it was natural to start using the term neuromorphic as well. So from 2008 on, the term neuromorphic also refers to this type of research activity and the community that is working on this research activity using emerging memory technologies and memoristic devices. Then in 2014, thanks to the DARPA Synapse project, IBM produced an impressive chip with 1 million neurons using digital circuits, so not really emulating the properties of real cells with the physics of transistors, but using at least asynchronous circuits. Some of us in the room were actually involved in the DARPA project and in IBM True North. This was really, as I said, an impressive achievement, but it was a simulation engine, or if you want, an accelerator for spiking neural networks. This was also done in parallel by other groups in Europe, in Heidelberg and in Manchester, with the Human Brain Project, the Spinnaker Project, and the Brain Skills Project. We're also developing simulators for neuroscientists and for simulating spiking neural networks. And more recently, since 2018, on Intel, also with the Loihi chip, started producing these asynchronous digital and spiking neural network simulators. So it's a more conservative approach compared to the approach of the basic research approach of Carver, Mead, and Misha, but still it's neuromorphic because it's trying to simulate spiking neural networks, so biological processes, with electronics. And so now the term neuromorphic, if you just wonder what is it about, it could be about basic research in building by understanding, or sorry, understanding by building. It could be about memoristic devices, but it could also be about computing with dedicated accelerators. And in fact, some people now argue that if you use dedicated GPUs, that is also neuromorphic. So there's a debate there. But what is nice to see is that with this conference, the community is realizing that it's important to combine all these approaches together. We've heard of the importance of this multidisciplinary approach. So by using the neuromorphic engineering approach, which is the one that is deeply rooted in neurobiology and neuroscience, by exploiting the physics of CMOS, but also now the physics of emerging memory technologies and other materials and devices, and combining analog and asynchronous, really there is a hope that we can go one step further close to natural intelligence using artificial intelligence methods and electronics. And ideally, we could deploy these and apply them to application-specific solutions for optimal computing. And as I will show you, one of the best domains where to use this technology is in so-called edge computing. We will see that. So now that I sort of covered the use of the term neuromorphic, we can go back to the original plan of this presentation to say how to bridge between artificial and natural intelligence. That is a very complicated task to do, because even the definition of intelligence, like the definition of consciousness, is something difficult. We know, though, that there is artificial intelligence which lives in the world of virtual, or if you want, the metaverse, anything that is simulated, and you can have games of Pong, you can have Atari games being simulated and being trained online through von Neumann architectures that run on large data centers. We've heard that this is an approach that is problematic because the energy required to train these systems and also to deploy them in inference is in the order of megawatts. And the improvements are not sustainable. And on the other side, we know that human brains using neurons and synapses, possibly also astrocytes and glia cells, are using very low power in the orders of tens of watts to produce intelligent behavior. So the term behavior here is really important. When we look at intelligence in the natural world, there's not only sort of abstract thought, but there's also things that are considered intelligent that involve interactions with the environment and producing behavioral outputs. So in order to try to address this problem of energy consumption, what we are seeing is that, okay, we know that the brain is burning much, much less than artificial intelligence systems. The brain is using spiking neurons. So if we go in the direction of using spiking neural networks rather than artificial neural networks such as deep networks or convolutional networks, maybe we can go one step in that direction. And this is what's been happening. So people are producing models of spiking networks with elements that are not just simple McCulloch-Pitts neurons or simple multipliers. They actually have a little bit more of the dynamics and the physics of real neurons in. And then dedicated chips, such as the Loihi I told you, are being designed to run these networks at lower power and faster than CPUs and GPUs. Then there is a huge engineering effort, and very impressive one, in scaling these things up with both. We have here recent examples of Loihi and Spinnaker 2 with SpinCloud. And the idea here also is if we scale things up, we will get better performance. So here, this is a bit of a provocative slide saying, if you look at what happened in the 90s, we should be very careful here that just scaling things up, just having millions and millions of neurons is not going to be a magic bullet that will understand us how the brain works or how to do low-power AI. On top of this, there is also the approach of looking at exploiting the results that we've been seeing in emerging memory technologies. So by complementing these pure CMOS attempts that we have been seeing, using now co-integration with memoristic devices, and using maybe spike-based learning rules, will go one step further. And this is true. This is a really important step to make. The provocative statement here that I would like to make is that this actually is a really, really tiny step. So here you see the scale is linear, and people might give you the impression that we are sort of halfway through. But in practice, there is many, many more steps to take to actually achieve this complementarity or to achieve the performance of biology, of natural brains. Not even human, even insect brains are very, very difficult to achieve. And so among these many, many steps, these quantum leaps that are required, there's, of course, technology development, going forward with memoristic devices, And combining member-stiff devices with CMOS is really an important development that needs still to be taken into account and to be developed. But in addition to that, there is also important steps in theoretical neuroscience and computer science to really understand how to co-design and integrate together the technological developments with the theory and the algorithms that can exploit the technologies being developed. And one very, very important step to make is to figure out first what is the right representation to use to represent signals and symbols for exploiting these technologies. It's not necessarily true that binary representation is the best one, or like one hot, single spikes are the best representation. So this is still something that needs to be identified and taken into account before actually building on top of that. Now, the type of simulations that we are running on these computers or accelerators are really useful for exploring the space of what can be done with software in spiky neural networks. But if we really want to co-integrate and exploit the physics of the devices that we are doing research on, we really need to think also at the level of different representations, not binary or software-simulated spiky neural networks. And indeed, we need to take into account the analog properties of the devices, in addition to digital, of course. One should not be a fundamentalist, one or the other. Another important point that is often neglected is time. In the natural brains, time represents itself. In software simulations, time, physical time, is completely decoupled from software simulation time. It could take, a few milliseconds to simulate a very complex evolutionary algorithm that in nature takes centuries, and it could take, weeks to simulate a protein folding that in biology takes milliseconds. So simulation time and physical time in computers is completely detached. If we want to reduce power consumption, having time as one important variable that represents itself is actually a very important and crucial point. And if we do that, then it will be also important to understand how to process signals at multiple time scales. With computers, this is not a problem because we always have access to the data whenever we need it. We can wait 1 minute, 1 hour, 1 week, we can always get it. But if we are doing a physical dynamical system that processes signals through time, then we need to have ways to store information across multiple time scales. Finally, this technology that we're using is essentially 2D. It's maybe 2.5D, whereas the brain is 3D. 3D integration is really an important key component for going forward in this, trying to bridge these two aspects. And another important aspect is active sensing and embodiment. Natural brains don't just get static pictures or buffers of data and then process those without taking any action. We continuously change the input of our data in order to do better inference. So we do active sensing continuously. And this is also an important step, especially to, as you will see, to take into account the fact that our underlying computational substrate is noisy and imprecise. So if we want to somehow overcome this imprecision, we need to change the input until we converge to a solution that is satisfactory. So as I said, this was maybe a provocative statement saying we are way, way behind, but also a positive note is that there are many, many interesting developments in all these points. And we will see many of them in this conference. I'm really, really excited to see the upcoming talks. We will hear about analog and representations. We will hear about time and multiple time scales. We will see posters, I know, that are addressing these problems or these issues. There will be a very exciting talk I'm looking forward to on 3D integration. And even today, this afternoon, there's going to be a very interesting talk on active sensing and embodiment. So it's really an exciting time in that respect. Now, this is the bridge that needs to be built in order to go from artificial intelligence to natural intelligence. And this community has been making steps in that direction. I just wanted to show you in the next few slides some of the steps that we have been taking ourselves in our lab and in our institute to build these types of neuromorphic systems. Again, remember, the type of the things I will show you are the ones that are more closely related to the Carver-Mead approach of neuromorphic engineering, really to try to emulate real neurons in order to, again, reduce power consumption, but also understand how neural processing principles of computation can be implemented with neurons and synapses. And people often ask, why do you need to actually build systems and go to the effort of understanding by building? And one answer is that there are existent proofs that are really, really convincing. And if you don't need to look at human brains or 10 to the 11 neurons and 10 to the 14 synapses. Even if you look at small devices, small computers that are in the head of the bee, you will realize that there is an amazing opportunity for understanding and building very, very intelligent and complex devices, artificial devices. And these computers that are in the heads of bees or in the body of the bee are really amazing. They weigh less than 1 milligram. They occupy less than 1 millimeter cube of volume. They have less than 1 million neurons, way, way less than the number of transistors we can actually put on chips. And the energy of any spike is really, really, really low, 10 to the minus 15. So if we want to reproduce this, the technology is there. But how can we actually build an artificial device that has the same properties of these animal brains? And some very nice design principles are the ones that were actually proposed by Sterling and Laughlin in their really nice book in 2017. Arguing that if we want to build things that have the same energy efficiency and same computational complexity, we need to use slow and noisy processing elements, which need to be variable. I will show you that it's actually not a bug, it's a feature. There is a requirement for variability. We cannot afford to have all-to-all connectivity. If we have strong restraints on the volume, on the size of the volume, or if you want in 2D, on the size of the area. So connectivity is expensive. We need to understand how to connect these devices and create networks that work when there's only local connectivity, or if you want small world network type of connectivity. Time multiplexing is something to absolutely avoid. If we want to reduce power consumption, we need to have massively parallel operations. So if we want to have 100 neurons operating, we need 100 physical copies of these neurons on the layout to operate in parallel. Having one core that is running very, very quickly to update the numerical equations of a neuron, putting them in memory, getting the next neuron, updating the equations, putting it in memory, and so on, is a recipe for disaster. It's just using von Neumann bottleneck. It will be using a lot of energy to move the data, and it's not going in the direction of bridging the gap between artificial and natural intelligence. Finally, the closed loop, the constraint of being able to operate in a closed loop, interacting with the environment in real time with closed loop interaction, also guides the development of algorithms. It's a really important design principle. We need to do this, of course, in real time so that we can interact with the environment naturally. And we need to do it with signal processing. The signals coming into these agents are real-world signals. They're analog, so we need to use the principles of signal processing, amplifying, filtering, bandpassing, and so on. And one important element in this recipe is also to use feedback adaptation and learning. This is the trick, one of the most important tricks that biology uses to compensate for the variability and inhomogeneity. So the main take-home message here is that there is no software algorithm that is detached from a hardware. It's not like you can create a network, run it on an ARM processor, on an Intel processor, on an FPGA. In this case, the hardware is the algorithm. The brain uses time evolution of the physical system to implement its computations. And the circuits compute by exploiting the dynamics and the natural time evolution of their substrate. So this is really something to take into consideration when trying to understand how to bridge the gap between artificial and natural intelligence. And we've been doing these types of chips. I already was doing them in 1994 when I was at Caltech, visiting Carver Land from Christoph Koch's lab. But we've been doing them also in Zurich. There is actually a long sequence of chips that have been designed. And all of these chips have been designed using these analog subthreshold circuits that implement the dynamics of synapses and neurons. So in weak inversion, using diffusion and Boltzmann statistics. We do try to slow down silicon. So the mobility in electric transistors and the mobility in cells is very, very different. But we can slow down silicon so that we can have time constants that are in the same range of biological time constants. And people usually ask, why do you want to slow down silicon if you can go so fast? I will answer that in the next slide. But we also then copy-paste, as I was saying. If we have, in this case, this was an old chip, we had about 32 neurons, so you can see 32 copies of the same layout along the vertical axis here. So all of these neurons operate in parallel. You stimulate them, they take time to integrate, and while one neuron is integrating, if you stimulate all the others, also all the others integrate their currents in parallel. But they are analog, and the subthreshold transistors are particularly sensitive to device mismatch, so there is a huge amount of variability. And again, you can think of this as a bug, and and engineers would like to somehow suppress this, or you could try to use it as a feature and exploit it. And I will show you how it's possible to exploit it. And this applies also to memristive devices, by the way. One way to try to compensate for this variability is to use adaptation and learning. I'll show you also those examples from the community, from many, many groups. By constructing chips in this way, by having this massively parallel operation, just by construction, they're fault tolerant. So if you think about space explorations or environments in which you're very, very sensitive to fault tolerance, this approach might be useful because most of these elements are working in parallel, if 99% of them. If one fails, maybe the accuracy of the network will degrade, but the whole operation of the chip will still be there. The chip will still be functional. So it will sort of smoothly degrade as more and more devices break or have faults. And as I said before, the idea is not only to use analog circuits, but is to embrace all the benefits of the technology available. So also to use fast asynchronous digital circuits. And the way we do that is that when all of this analog processing is going on in the synapses and in the neurons, as soon as a neuron spikes, we convert that spike into a digital word, which with the address of the neuron. All the neurons have an address on the layout. So as soon as a neuron spikes, the address of that neuron is sent on a digital bus as fast as possible, without a clock. It's self-clocked in an asynchronous way. And then there are routers, arbiters, asynchronous digital circuits that can manage the communication of these addresses, these spikes, and, for example, produce multi-layer networks, recurrent networks. You can have one sensor that can fan out to multiple destinations. You can have multiple sensors that can merge their spikes into one single receiver. And you can use all of the sort of digital toolboxes that are available to manage these trains of digital spikes. Once the spikes reach their synapses destinations, they are converted back into currents, and the frequency of the spikes determines the amplitude of the current. And so then we can do, again, signal processing in current mode with subthreshold analog circuits. So this is how we can bridge the best of both worlds, analog and digital, in these types of chips. And we've been, as I said, we've been making these for many years. One of the more recent ones is, so the original chips were done when I was at Caltech in 2-micron technology. That gives you an idea of how old I am. But now the more recent ones, we've gone through 350 nanometers, 180 nanometers, 65. Now this one here, you see an example of a layout in 22 nanometer technology using FDSOI. And this is just a chip that has about 1,000. It's a 3 by 3 millimeter chip, but it has 1,000 neurons. So we are riding the wave of Moore's law. By having smaller and smaller transistors, we can put more and more neurons on a small size chip. The problem with analog is that capacitors don't scale as well as transistors, so we still have to pay the price of area. If we want to have 256 copies of the neurons, they do take up area, so that's the price. There is no free lunch. We do have low power, but we do pay with using a large area for a neuron and an array of neurons. The other big area-consuming part of this chip is actually the digital circuits that are routing the spikes across neurons. In fact, if you zoom in any one of these pixels, which are these neurons, and if you look at the ratio between analog and digital circuits, you'll realize quickly that the digital circuits take up most of the area. They're about more than 80%, I think 86% of the area is for SRAM and TCAM cells that contain the address of the synapse of the neuron that each synapse is listening to. So if there is a match, whenever one neuron on one core or another chip spikes, it will broadcast its spike to all the synapses. The ones that have the right tag will then receive that spike and establish the connection between the presynaptic and the postsynaptic neuron. This is TCAM cells are taking up more than 12 transistors, SRAM more than 6 to 8, depending on the implementation. The hope is that if we can co-integrate CMOS with memristive devices, we can greatly reduce the size and in the same area greatly increase the number of neurons. So we could take advantage of the density. The advantage is not going to be that big because each synapse in any case will have other transistors. So it's not going to be a very, very dense 1T, 1R crossbar. But still, we will be able to take advantage of the smaller size and the non-volatility, maybe the intrinsic stochasticity properties of the memristive devices, and all of the other features. So giving up the density argument is not a failure. It's just only one of the many advantages that these devices have that we will still be able to exploit. The other important part, as I told you, these circuits in subthreshold, they operate below 800 millivolts, so they're in the order of hundreds of millivolts. They have currents that are in the order of pico to nanoamperes. So the heat density of any one of these areas on the chip is very, very small. And if we are going to explore 3D integration, we've been collaborating with Sealeti for monolithic 3D integration. It's not going to be a problem of having more than 2 layers. Standard digital technologies can only, for now, have only 2 layers because you need a heat sink on the top and a heat sink on the bottom. And if you have more, the heat density will just melt all the devices that are there. So if we don't do any special tricks, we can do more than 2 layers using very, very low power circuits. But I hope we will see later during this conference that there are ways of representing signals that can allow us to go into more than 2 layers with very elegant representation and neuromorphic approaches also. And of course, these routers, we will also see colleagues have been working on hierarchical routers. We will see how it's possible to create routers that implement small world network connectivity. So whether you have multiple cores on a single chip or multiple chips on a single board, it's going to be easy to tile all of these elements together and create complex systems by scaling these systems up, either on a single chip or multiple chips on a printed circuit board. So we know how to do these things. There's the community, our colleagues have been doing these, ourselves included, for many years. Now, what can we do with these chips? We have these arrays of neurons. They are inhomogeneous, they're variable, they're noisy, very imprecise. So what's the point? Can we do anything with them? And I wanted to show you that indeed there is some hope from biology that we can use this technology for real-world practical applications, really something that can be sold, not only shown on a paper in an academic environment. And as I told you, the biggest problem and criticism that comes from industry or from colleagues that work with standard deep network approaches is the fact that these chips are imprecise and low precision. In fact, you see here, this is data measured from one of our chips. Each core, as I told you, had 256 neurons. So this is just applying the same input current to all the neurons on the same core. The neurons, you see the analog dynamics, the temporal dynamics, they will start to slowly integrate over milliseconds, so we can slow down silicon. They integrate and they spike. But the timing of the first spike is very variable because each neuron is slightly different from each other neuron. And in fact, without trying to optimize for reducing mismatch, just by making adequate circuit designs, with a compromise between making them small but also not too noisy, the typical variability that we get is about 20% coefficient of variation. So the average, the standard deviation over the mean is about 20%. Can we do anything with this? So I would never put this like in airbag controller or in an Excel sheet to control my bank account. So is there a way that we can actually use it to do something accurate? Well, the first thing that comes to mind is to use averages. If you just use the law of large numbers and pure statistic, if you just average over n neurons, you can reduce the sigma by square root over n. So that's one very, very simple trick that can be done. Can we quantify how much we can do that? I will show you. But also there's theoretical neuroscientists and computational neuroscientist models that show you that if you combine excitatory and inhibitory neurons, and if you combine the nonlinear properties of these synapses and neurons together, you can actually go beyond the square root. You can actually reduce the sigma by a factor of n, which is much more powerful. So this is just to show you again another measurement of average activity from these 256 neurons. If we stimulate them now, not with a simple current, but with spikes in input through the synapse, which then gets integrated by the soma, and then the soma produces spikes in output, the frequency to frequency plot, FF curve, is shown here. And you can see on the gray the gray plots here are all the single neuron responses, and they're all over the place. It's this, as I told you, this 20% coefficient of variation. But if you take the average over these 256 neurons, you see this very nice ReLU curve, which is very, very accurate. So again, you pay a huge amount of price because we're using a whole core, a huge amount of area, to get a precise, accurate ReLU function. But we can at least get that. And here in the inset, by the way, this is data from real neurons, from biology. So here, if you inject current into pyramidal cells of a cortex circuit, I don't remember if it was a mouse or a cat cortex, you get similar type of properties. So again, look at the scales and the numbers. We have similar firing rates. We can slow down and reduce the firing rate of the neurons, so reduce power consumption, as much as in biology. And also biology faces the problem of variability, and we look at biology on how to actually solve this. If we want to quantify what is the bit accuracy of this operation that we're doing, we can convert that. If you look at the coefficient variation, you can convert that into equivalent number of bits. And now here is showing you what you gain by having populations or clusters of 2 neurons, clusters of 4 neurons, 8, and so on. And I told you the coefficient of variation of 1 or 2 neurons is about 20%. You can either integrate over time. So if you accumulate spikes and you integrate over 20 milliseconds, 50, 100 milliseconds, you reduce the sigma. But you can also integrate over space. You can have clusters of more. And in the coefficient of variation is written here in numbers, and the equivalent number of bits is color-coded. So if we would like to have a neural network with, say, 8-bit accuracy, we would need to use 16 neurons, I believe, with maybe 100 millisecond temporal integration windows. This is something that can be changed at runtime. So if we are doing something very coarse, but we want a response very fast, we can increase, decrease the temporal integration window. But if we want to accumulate evidence and get more and more and more accuracy, we can integrate over time longer and reach all the way 0.9 coefficient of variation. So the limit is 14 bits. In order to get more than that, we would really have to do good circuit design, the standard engineering approach, but that would require increases in area. And of course, the other trick that biology uses is not only averaging, but by the way, in cortex, also biology uses populations of neurons to represent signals. But the other trick is to use learning. So learning is something that you all are aware of. Probably everyone in the room knows about spike timing dependent plasticity, or STDP. This is a very popular and very handy learning rule that looks at the timing of the spikes and changes the weight depending on the difference between the arrival of the presynaptic and the postsynaptic. This was a rule that was found in hippocampus in 2018, I believe, by Pu and by Markram independently. It was then adopted by computational neuroscience, sorry, 2008. Yeah, please correct me if I'm wrong. In computational, or 1998, I'm going back, sorry, I'm going back by decades. I think it was 1998. And in computational neuroscience, it was adopted quickly, but then quickly also criticisms came about the whether this is an artifact or it's really the mechanism that biology uses, and that there are other mechanisms for learning that would explain STDP, but would also be more powerful. And also theoretical neuroscientists, theoretical physicists have all proposed new rules that go beyond STDP. So this is a plea to the whole community, just Please be aware that there is much more than STDP, and these new rules, from decades now, are showing how you can still use the timing of spikes, but using additional state variables to improve the performance of your network through learning. And the nice thing about all these rules, both STDP, but also these new ones coming from theoretical physicists and neuroscientists, is that they are very hardware friendly. They do require redundancy. This is something we have in VLSI. We can make many copies of our neurons. They don't require 32-bit floating point. They actually can work with 1 bit. They can, if you have bistable state variables, bistable synapses, or if you want multistable, 2, 3, 4 bits, you can still get very, very high accuracy in your pattern recognition performance. But if you do have this bistability, it's important also to have variability. So variability from these papers, from these authors, is a strict requirement. It's not something you have to get rid of. It's something you need to implement. And variability is something we get for free in memristive devices in CMOS. Then there's the question of how can we control the type of variability. That's something. But at least it's there. It's not as expensive as in digital, where you would need to have random number generators per synapse, which are very, very expensive in terms of area. The other thing is that these state variables, even though they can be bistable, the internal variables should be analog and should be updated with continuous time. You should not discretize time like with clocks. You need to somehow let time represent itself. If you have a leak, you need to have something that counts how much time it takes for the variable to leak. And if you wanted to do it with digital, you would need to have a very high frequency clock if you want to be precise in the leak. So analog is another requirement from these rules. And if you're doing mixed signal analog digital neuromorphic circuits, this is also there for free. There's been many demonstrations of chips that actually can implement these learning rules. The plot that you see here is actually data from one of our chips that is implementing a learning rule that was proposed by Brader et al. In 2007. It basically looks at the timing of the presynaptic spikes and the state of the membrane potential. And depending on those two conditions, it will either increase or decrease the weight with a leak that will make it stabilize it above or below in a low, long-term potentiated or long-term depressed state. But our colleagues have been making also many, many variants and other implementations of other learning rules. Even in this conference, you will see in the poster sessions new and more advanced learning rules that are being proposed that are either implemented in hardware or compatible with the hardware circuits. And one thing I would like to point out that can be done with these analog, memristive, and CMOS devices that is difficult to do with CMOS unless you explicitly simulate noise, is to use bagging techniques. So again, there is always a criticism whenever you go to spiking, whenever you go to these analog, noisy, imprecise circuits, you pay with accuracy. In machine learning community, everyone is looking accuracy, accuracy, accuracy. So here it's true. If you're using one of our silicon neurons and you use it as a binary classifier, for example, to distinguish between a digit 3 and all the other digits, you will have performance that is laughable. It's like 32%. And in machine learning conferences like NeurIPS, they kick you out of the conference if it's not above 98%. So this is really something that is not even going to be considered by machine learning experts if you show just one noisy, unreliable classifier with one of our neurons. The nice thing, though, is that in the 90s, again, 97, it was shown that if you have many inaccurate, or if you want crappy classifiers, and if they are independent, by having ensemble techniques, by combining these classifiers, the accuracy can be increased, and the error decreases exponentially with the number of classifiers. So this theory is something that's really, really powerful. It has not been used or exploited in standard machine learning community because machine learning software algorithms are bit precise. They are not independent, inaccurate classifiers. They just have one classifier that is highly, highly accurate. But here, whenever we have our 256 neurons, we can have 256 of these inaccurate classifiers. And as you see from simulations that actually Fabio Stefanini did in Zurich, the accuracy follows the theory. There are correlations between these neurons, so they're not perfectly independent, so it's not purely exponential, but at least it goes in the right direction of increasing the accuracy with the number of classifiers used. By the way, I will share the slides with everyone. Whenever you see things that are in square brackets, in the slides, you can just click on them, and it will take you to the paper or to the source. So it's just for convenience. All these papers that are mentioned are going to be easily available through the slides. So this is just to say learning can also, in addition to using populations of neurons, learning can also be useful for improving accuracy of your networks if you use mixed signal, analog and digital, and don't just stick to pure digital software simulations. So this is basically what I'm saying here, that in addition to using populations of neurons in learning, you can do also more. This is the same idea that was used from the early developments of digital technology. Instead of using single transistors to be able to build complex compilers and solve complex problems, the idea is to look at computational primitives and to have a hierarchy of primitives, or if you want in computer science terms, a stack of elements that can allow you to then build complex and solve complex problems. And biology also does that. If you look at single neurons, it would be impossible to try to think of how to connect single neurons together to solve a very complex, if you want, cognitive problem. Biology also found the trick. If there are, for example, in the cortex, there are these prototypical circuits that are, once nature found the trick to use these circuits as attractors or winner-take-all networks, it repeated the same structure across the whole cortex, across the whole brain. So if you look at visual cortex, you will find some type of connectivity diagrams. If you look at somatosensory cortex, olfactory cortex, all types of cortices, auditory cortex, you will find the same building blocks that then can be used like a sort of an op-amp or a logic gate to combine elements together and build complex processing systems. And these primitives, the community, again, of theoretical neuroscientists has been identifying them, going from attractor networks, EI balanced networks, winner-take-all networks. They are all flavors of the same idea of a canonical circuit in which excitatory neurons, these triangles here, are connected through inhibitory neurons, the circles here, with positive and negative feedback loops. And by changing the properties and the weights of these connections, you can get different behaviors, from filters, from continuous signals, to manipulating symbols, for example, playing chess or Sudoku or other problems. The same thing is by putting together these networks and combining them in different ways, you can build so-called relational networks. And then a slightly different flavor is combining these to create oscillations. They can also be used to drive motors and create central pattern generators, but also bind things from different cortical areas together. Like, if the sound of something and the vision of something belong to the same object, they will probably be in phase with these oscillations. And finally, neural state machines is something I would like also to highlight and to show you. I'm getting close to the end, just to show you what can be used in neural state machines with these chips. If you're curious about these attractor states and plasticity and learning with dendritic plasticity, calcium-based plasticity rules, there is actually a poster by Mariada that is going to go into the details of this. But now I just wanted to show you how can we deploy these chips. I told you now it's possible to use biologically inspired techniques to do robust computation. Where do these chips make sense? They cannot replace GPUs. I don't think that's a good strategy. But going in examples of applications that need to process signals with low latency, where maybe you cannot connect to the cloud and you need to have a small, compact, low-power device, for example, at the edge, where you need to process data directly from the sensor, this is the most promising application area for this type of technology. And we are seeing that this type of trend is coming to our time, not only being pushed by this community, but being pushed by the whole ICT industry. So there are other papers and companies saying that we go from the eras of mainframes to client servers, where there were big desktops on our desks, to having a lot of power in our cell phones, in our pockets, now to having small chips that can do very, very dedicated specific applications. For example, measuring your activity, measuring if the fish has gone bad in the refrigerator, or measuring how you use your furniture. All of these are dedicated chips that can only do that thing. They cannot invert matrices or solve Excel sheets, but are very low power. So this technology that we're building actually fits right nicely into this edge intelligence era. And in our institute, we've been trying to see if we can apply our chips to these types of problems. And we've been focusing, one example I will show you is focusing on biomedical signals and medical applications or wearable applications. So again, if you're curious, you can go to the details by clicking on these links. But we've been looking at, CPGs, heartbeat anomaly detection, trying to decode the muscle activities, EMG, for example, for controlling prosthetic devices, without having to wear a backpack, with a small lithium battery and a chip that can do the decoding. Detecting in the EEG if you have epileptogenic zones that create seizures, again, using these low-power chips. And the latest one that is actually has just been submitted 6 days ago to BioCAS is a neuromorphic heart rate monitor. So I'd like just to show you how to use these neural state machines that I mentioned to monitor the increase in heart rates across hours, even though our chips have time constants of milliseconds. So our capacitors, they leak away after 500 milliseconds at most, probably 100 milliseconds. But we can do that using these state machines. So a state machine is really a mathematical framework that allows you to say if you're in one state and you get one external input, if, then, else. So if you're in one state, you get one external input, you go in one direction, and otherwise you go in another. This is an example of the most simple state machine that one can think of, where if you're in state 1 and you get the symbol A, you go to state 2. If you're in state 2, you get the symbol A, you go back to state 1. And otherwise, if you get B, you stay in the same state. This can be done with spiky neural networks. It can be done with winner-take-all networks. They're represented here by these drawings that actually Emre Nefci made 12 years ago. And the input, A or B, is also a winner-take-all network. It's either A or B, so A wins or B wins. And that is also represented by this. All of these can be circuits on a core or chips that implement spiky neural networks. And in fact, Emre, that's what he was doing while he was a student at INI. He was connecting these chips together. He was giving the input to the chip. These blue or purple bands represent the input. The input population would start spiking, and it would trigger the switch of the winner-take-all. So the winner, as soon as it saw, if it was in one state, it would flip in the other. If it was in the same state, it would not flip. And then again, if it was in the other state, it would flip again. So you can see here from the activity that this chip, where you see the average spiking rate and the spikes on the x-axis, represent the state transitions. This is how we can get these neural state machines to work. And now, just to show you how we can monitor heart rates, we've been implementing exactly the same framework to data coming from measurements of heart rates, filtering those in 4 different bands, low heart rate, intermediate heart rate, high heart rate, very heart rate, and then encoding those with states, where you have low state is relaxed, intermediate state is state 1, other state 2, and then the very, very strong heart rate is alarm, state 3. And we can do this with these populations of neurons connected in this way. We have winner-take-alls, excitatory, inhibitory balance networks, and so on. Again, all the details are in Emre's paper, and now they will be in the BioCAS conference paper. If it's accepted, it's still under review. And this is showing you what the data looks like. So if we send in spikes in the input population, in the case in which we only have the winner-take-all activated, this is every time you send a small kick to the winner-take-all, it will flip, and it will stay there. So it will just select, if you send the input 0, it will go to state 0. If you send input 1, it will go to state 1, and so on. So this is the activity of this sequence of inputs over 42 seconds if you only have a winner-take-all network. As soon as you connect the state transition populations, so you implement the neural state machine or the finite state machine diagram, you will see that the same input increases go to the next state only in cases in which you have monotonic increases. If you have non-monotonic increases, there is no state transition. You just stay in the old state. So this is the difference between previous and next. So here you can basically set an alarm only if consistently your heart rate is going up and up and up. And this is something that actually happens in elderly people when they go into an agitated state over hours. So it's not something you can do with a few millisecond time constants. You need to have something that holds the memory for long periods. And the data down here is actually here you see in the inset, this is the electrocardiogram data. Again, over hundreds of seconds. And in this case, the subject was running. We did not have access to elderly patient data. And you see that we do reach an alarm state because the heartbeat increases monotonically. And even if there's noise and variations, it's robust to those variations. And in the case of the subject only walking, you do not reach the alarm state. So this is just to show you some new slides compared to many of the ones that I used before that are old, where we have new results that actually put all of these things together and can create very reliable and robust outputs, despite the fact that we're using very unreliable computing substrate and very noisy. So finally, to conclude, we are now in this era where we are realizing we need to combine the various disciplines together, from computer science to neuroscience to device physics, material science, and CMOS engineering. We are in an era in which big data needs a hardware revolution. This is already an old perspective from Nature of 2018, but it's still true that we heard there is this unsustainable increase in energy consumption if we keep on using the same approach. And really, the small print here says that even though software companies, and if you look at NeurIPS and Archive, software research developments are making the headlines, the real potential impact, let's see, research on computer hardware could bring bigger rewards. So we really need to start looking at how to implement algorithms that are matched to the type of hardware technologies that we are developing, and not detach the software from the hardware. And conventional AI, as I said, is really asking us to do this. The standard approaches are not sustainable. In parallel, we have really promising results from new emerging memory technologies that can now finally be co-integrated with CMOS. Neuroscience has been making tremendous progress in learning models and computational models of computation. We will even see, just after this talk, some amazing results. And meanwhile, hardware implementations of spiking neural networks, hardware implementations of neuromorphic systems are starting to show that they can actually be used in the real world. Some startups are coming up. They are actually successful. They're starting to sell products using this unreliable technology, and we really have some hope that we can make an impact. As I said, not to replace GPUs, but to complement them in applications in which GPUs are an overkill. They're burning too much power, maybe for very, very simple problems. So putting these things together, this is the perfect time to follow this neuromorphic computing and engineering approach that this conference is really bootstrapping. So I'm really excited about it and really looking forward to the next talks in this conference. So I'd like to really acknowledge the group in Zurich that has been really helping the whole team actually doing all of the work, the various funding organizations, but most of all, I would like to thank you for your attention.
Thank you, Professor Indiveri, for this great talk. I'm a device engineer, so I was very happy to hear that you embrace variability in new devices. And people who work on this field, we have trouble repeating results exactly, and so having some leeway there is a good thing. We have time for questions, and we have these stand-up microphones here in the audience. So if you have a question, please go to one of the microphones. Hi, Abu. Yeah, why not? I prepared questions, but go ahead. Please state your name and your affiliation as well.
Yeah, my name is Abu Sebastian. I'm from IBM Research. Thanks, Giacomo, for the very interesting talk, as usual. I just want to ask you a little bit about the diagram that you showed, right? How to go from natural intelligence to artificial intelligence in terms of the power, right? As technologists, are we kind of overstating our importance? Because if you plot that same thing in terms of energy, probably we are not that far away, right? Because we are comparing like a 10-watt brain, but that of course runs with 10 hertz, right? So clearly, if you have that x-axis in the energy, then probably we are not that far away, and maybe with some tricks like in-memory computing, we may come even very close. But indeed, there is a big chasm between natural intelligence and artificial intelligence, and that is in terms of the reasoning. These sort of things, right? And this famous test that Steve Wozniak said, right? That you walk into a kitchen and then, unknown kitchen and make a cup of coffee, right? That's kind of the problem. So which means that we have a huge problem with something like reasoning, how do we represent information, how do we compose them, these sort of things. And how can neuromorphic engineering give some answers in that regard? Because in terms of energy, I'm not so convinced, because he also gave the example of the B, it is 1 femtojoule per spike, but the modern processor does 32-bit addition with 20 femtojoules, right? So we are not that far away in reality. But I find a big chasm on the other aspect, and I'm curious what your thoughts are.
Yeah, thank you, Abu. Yes, so concerning the power argument, the proof is in the pudding. One thing is to talk about energy efficiency and how many inferences per second or how many max you can do per inference, and looking at the energy. Of course, the inverters are actually as power efficient as neurons. If you look at the energy of one inverter, is in the order of 7 picojoules, and neurons are about 3 picojoules. So we're in the same ballpark. What counts is, in the end, how long does your battery last on your device to do some intelligent behavior. So even if the numbers of your Mac operations are in that range, everything else at the system level is not going to make your battery last more than a few hours if it's on a very elaborate, complex machine, or maybe one day, if not. So it's not enough to look at the single element in the system of the energy consumption of the single element. One really needs to think at the whole level of the system, the connectivity, the length of the wires, the small network, the number of wires, and so on, and how many pins you have to charge and discharge. So the energy is not only a question of the single device or the single silicon neuron versus digital, analog versus digital. It's really looking at holistically from the algorithm to the mechanics, to the packaging, to the finally down all the way to the computational and memory elements. But for the other argument is also saying we need to look at biology. So I showed you now this example of these state machines. The paper that Emre actually wrote in 2013 was titled "Synthesizing Cognitive Systems," so cognition. How do you reason about solving a Sudoku problem, solving the Tower of Hanoi, or playing a card game? And it's been shown, not by us, but by other computational neuroscientists really working on neuroscience, that spiking neural networks can do that. If you combine these winner-take-all networks together, you can see the populations of neurons transition from one tentative solution of Sudoku to another tentative solution to another until you converge to the real solution. So it is possible to have cognitive problems being solved by spiking neural networks, on one hand. On the other hand, we do have the technology to implement these spiking neural networks. So we are making small steps in that direction. But as I did point out, there is many steps to make, especially to get to the point where you have a robotic agent that has the dexterity of a human. That's even longer. So getting to interact with the environment is really a complex task.
Good. We have a question here, and then Ralf Schlüter.
Thank you for your nice talk. I'm John at the Max Planck Institute. So I'm interested in your later part of your talk about the heartbeat monitoring and other real-life applications. I'm curious, are you making them into real products for markets, and what's the difficulties between research scale experiments and real-life products? Thank you.
Yeah, it's a similar logarithmic plot here. Going from the proof of concept or the prototype to actually the product is a huge endeavor. It really is a huge effort. As I said, there are startups. I'm interested in basic research, so I'm not involved in developing these types of devices into products. But there are companies both in the Netherlands, in Europe, now also in China, trying to follow this approach to make products for practical applications. In this case, it wasn't for heartbeat, but I know that there were cases with PPG on ear tags for animals, for monitoring the heartbeat of animals, and they are developing a product in that direction. So it is, as I said, something that is being explored for making products. But it does take, going from a proof of concept to a prototype that can convince a customer takes 10 times the effort. And then going from the prototype to the product takes another 10 times the effort. So we talk about 100 person-months if it's 1 person-month work for like a biocast paper. So it's a really, really big effort that I don't think universities have to take, but startups are convincing investors to actually put in hard money to go in that direction. So it's happening. It takes a lot. It takes a lot of effort.
Thank you for that comment. I know we have some people from the funding agencies here as well. It's always good to understand, to have a common understanding of this issue. There was a question there, and I hope we can fit you in, but if not, the speakers will be here after the session.
So do you hear me? Yeah, okay. So I have a question about the ensembling aspect. So when you start ensembling, you also trade, say, the advantage of energy efficiency in a way. And on the other hand, it also says possibly something about the numbers when we compute. So when we compare how many neurons do rate-based methods have and how many neurons do you need for spiking networks. Could you say something about that? Thank you.
Yes. So first of all, the trick to have large networks of spiking neurons, with millions of neurons, and still have low power is to impose sparseness. So there are, again, not from our group, but from theoretical neuroscientists, Sophie Deneuve, Christian Markens, show that if you train networks, for example, a simple problem of encoding a signal, if you want to encode with very high accuracy a sine wave with a network of spiking neurons, if you had to use high firing rates and lots of neurons, you would lose the power advantage. But it's possible to train them to be very, very sparse and to have like one single spike will push things in the right direction and then another spike will push things in the other direction. And they show that you can get this with, you can have very, very high accuracy with very low firing rates and with relatively small number of neurons. So again, the solution to this problem comes from theoretical neuroscience. And as I said, there is a proof of existence. We are a proof of existence that this is possible to have millions of neurons, but have 10 watts, 20 watts power consumption. The other thing about the rate-based is similar by having low-pass filters with essentially synapses that encode many, many spikes. It's possible then to get these analog waveforms that are equivalent to rate-based units. But because these spikes are sparse, they are lower power. And remember, I didn't mention it, but all the circuits that we are designing, and we and the colleagues also in this room, are passive. So if there is no spike, there is no active component. So the only power consumption that you have is leakage current, dark current. But if there is no activity, so if your robot closes its eyes, if your device is in a dark room, it will just burn leakage power, the minimum. And as soon as there is a spike, the spike charges up a capacitor, which then powers up the circuit. So the data is powering up the circuit. And that's also the other trick that we have for reducing power consumption. With ReLUs, if we had to do that with op-amps, every op-amp would be always on, whether you have data or not. So it would be more difficult to have low power with ReLU-type neurons.
Well, thank you. In the sake of time, we cannot have more questions now. I'm sorry. I know there are more questions, but please come and see Professor Indiveri after the session. Thank you again for your great talk.
Thank you.